So recall that there are three important patterns when we talk about the biogeography of islands: species area, species isolation, and species turnover. The first is the most concrete one, namely that there is this sharp relationship between area and number of species. They are positively correlated with each other. As one increases, the other one increases. Species richness increases as islands get larger. There is the species area equation that relates these two things, and the two constants you see here, C and Z. C is, it turns out, is going to be the intercept on the y-axis, and Z is going to be the slope of this line. S and A are what you already know, the species richness, counting of species, and A is the geographic area of the islands. And just a quick look here, even if you don't know the names of all these islands, Redondo, Saba, Montserrat, etc., all the way up to Cuba, these are islands where they are plotted as progressively larger and larger areas. And then notice that as area increases, you get a positive slope to this line because the y-axis is number of species. The second is the relationship between species and isolation. The farther an island is away from a larger mainland, the less species it's going to have. This is going to relate to the immigration and extinction there. So an island that is just 100 kilometers away from the mainland is going to have more immigrants from that mainland than an island of the exact same size that might be 1,000 kilometers away or 2,000 kilometers away. And so in this graph right here, you see the distance from New Guinea, which is taken as a large mainland. It's a very large island. And then instead of species richness here, you've got a proxy for it in degree of saturation. Basically, the closer you are to New Guinea, the more species you have in common with New Guinea, lots of them. And the farther away you go from New Guinea, the less species you have in common with New Guinea, and therefore the less number of species total. And then finally, the third pattern is that despite immigration, extinction, all of this, the fact that the areas stay relatively the same, the isolation stays relatively the same, means that species turnover is going to keep taking you back to a constant number of species. So, for instance, a turtle might go extinct on a particular island, but it then would be replaced by maybe another turtle, but maybe a completely different herbivore would do it. And so that if you'd sample an island at one point in time and say it had 35 species, and here's the list, you could come back sometime in the future. There would probably also be about 35 species there, but there might have been turnover, meaning there might be new species there. I made a point last time of saying that MacArthur and Wilson, these two guys, came up with this very important theory that has guided a lot of our ideas on islands ever since. And so let's look at it. They set this up as a simple graphic problem with a solution. So the basic model for species richness. Species richness is plotted on the x-axis there. Notice if you go from left to right, you go from 0 species, which is the minimum, nothing, to P, which they list as the maximum number of species on a given island. So P is the number that is available to colonize from a nearby landmass. So let's say a nearby landmass has 100 species on it, then this island, which is somewhere out separated by water from it, can potentially receive up to those same number, 100 species there. Let's look at the immigration rate. The immigration rate is the rate of arrival of new propagules, that just means individuals, of species that are already present on the island. So it ends up graphing out as this negative sloping line right here, and notice that at 0 number of species, the immigration rate is at its maximum. So if there's no species there, then the rate of arrival of species that aren't already there is at its maximum. Anything that arrives there is going to be new. Contrast that with the other end of the extreme here, P. P is where this immigration rate is at a minimum. Let's say this island does happen to have P. That same 100 species that were present on the mainland, they're also on that island. Well, then the immigration rate is 0, because anything that arrives will not be a representative of a new species. So this negative slope like this. To summarize, the rate of immigration must decline from some maximum value when that island is empty to 0 when the island contains all of those possible species that also exist on the mainland. Now let's consider the other side of the equation, extinction. So on small islands, well, everywhere, but it's particularly on islands, species are very likely to go extinct. You know, they are geographically isolated, they're small, the populations on them are small, and so it's very common for there to be local extinctions or extirpations. And so the line over here plots the rate of extinction. And notice the rate of extinction, the loss of existing insular species, it is at a maximum when the number of species there is at a maximum. If you have all 100 species there, then the rate of extinction, the potential rate of extinction, is at its highest. They all exist there, and so the potential loss is highest. That then slopes all the way back to 0. And again, this is a duh moment when it makes particularly good sense. If you have no species on the island, well then none can go extinct. And so you've got this rate of extinction, rate of immigration here. Summarizing extinction. As an island fills with species, the number of island species that can suffer that extinction also increases. So going across on this x-axis here, as you add more and more and more species, the potential for any of those species to go extinct increases up to some maximum. Now here's where the equilibrium comes in. The point where the immigration equals extinction, and those are labeled as I and E, where they are equal, that is the equilibrium value. If you have a point where immigration is equal to extinction, you can drop straight down, and that number is called the equilibrial, sorry for the name, it's their term, the equilibrial number of species, or S hat or S caret, depending on what you call the little symbol above the S. If this island ecosystem is disturbed in any way, a big storm, big extinction event from a tsunami or anything, or a huge pulse of immigrants from the mainland, what happens is, over time, what's going to happen, it will end up returning to this equilibrial, optimal number of species on that island. What causes this equilibrial number of species is a very particular rate of turnover, the third pattern that MacArthur and Wilson incorporated into their model. And so they have defined something as the equilibrial rate of turnover, or T hat, which is over here. And notice it plots on this y-axis on this particular diagram. So equilibrial number of species plotted up to the point where immigration equals extinction, shoot over to the y-axis, and that value is this equilibrial rate of turnover. now let's mess things up slightly. What if you do have a period where the immigration rate is greater than the extinction rate? So you're going to have less species than S prime. Or a better way to say it is that if you have less species on an island, lower than this equilibrial number of species, then the immigration rate of potential new arrivals is going to be higher, and so therefore the number of species is over here. If you then plot that up, shoot it over here, the rate of turnover is increased. Again, this whole model exists to always return things to this S hat number where immigration equals extinction. Doing that will make this turnover rate decrease as well. If you have a situation where extinctions are greater than immigration, then you are looking at a situation where you have more species than the equilibrial number. So let's say we have on this island more species than our S hat, then just by the way this is plotted, the potential extinctions here are greater, and you also have a higher turnover rate. Okay? Again, both of these, whether you have immigration rates exceeding extinction or extinction rates exceeding immigration, act to increase turnover and drive the system back to this equilibrial number of species. Now, MacArthur and Wilson, on the back of their cocktail napkins, decided to incorporate species area here. And in this sense, you've got two different types of islands, size of islands, small and large. We also, well, when you're looking at small versus large, you have different rates of extinction for smaller versus larger islands. And this is sort of a logical thing. Smaller islands, they're smaller. You have less individuals on that island. It's very easy for a local extinction from some event. A large island has more places of refuge, more places where perhaps the extinction causing event will not sort of have a negative effect on them. And then you're simply going to have more individuals there. And so this slope of this line is different. A large island will have a lower slope. A small island will have a steeper, a higher extinction rate. The ultimate result of this is, again, the steeper rates, steeper curves for these smaller islands. They also incorporated species isolation, and that's over here as far as immigration is concerned. And so you have far islands and near islands. The rate of immigration for islands that are near a mainland is higher, and therefore this is the steeper line over here than it is for islands that are much farther away. The immigration rate is going to be lower over here. So you have steeper curves for nearer islands. So we're going to have some relationship now between near islands, far islands, small islands, large islands, and some combination of these things. Notice that these intersection lines end up plotting different values or different sort of systems of numbers of species here. I'm going to get right back to that in just a bit. And here then we show that farther islands will have a smaller equilibrial number of species. So here's a far island, and where it intersects either the small island or the large island, notice it is deflected to the left, closer towards zero. Then the opposite is true for nearer islands. This then makes the prediction, and here's the summation of this whole thing, that the number of species on small, far islands is lowest. What is greater is the number of species on small, near islands, which are roughly equal to the number of species on large, far islands, and then all of them are dwarfed by the number of species on large, near islands. Again, this makes sort of logical sense, and this is what they showed. So the top part of this, the relationship between number of species and whether an island is small or large or near or far, that's what you need to remember. The turnover rates then, remember we get that by sort of plotting up to where these things cross in the scissors diagram and over here. The turnover rates reflect this as well in a different pattern.